This lesson is the second of 3 on the Inertial Reference System, or IRS. In the last one, we said that there were 3 main characteristics which define what we now call an IRS, which make it recognizable in first-generation standalone INS. These were greater system integration, the use of ring laser gyros, and much greater computer power. We will now go on to consider the second of these, the ring laser gyro. The biggest single change of technology in IRS is the use of non-rotating gyros. INS used tuned rotor gyros, that is, spinning discs, which are the same type as all the other gyros you have studied until now. By contrast, IRS uses ring laser gyros, which have no moving parts. Over the last 40 years, it has become possible to miniaturize lasers down to a size small enough to use in aircraft. Look at the pattern of the laser light, which is shown in yellow here. This is a picture of an IRS inertial reference unit. It is mounted in the aircraft with this end facing the front. You can recognize that laser light pattern. 2 of the laser gyros are easy to see. Here is the gyro which measures pitch. This one measures yaw. But you can also see a little spot of light here. This is the 3rd gyro, set at right angles to both the other 2. This one measures roll. These ring laser gyros are not gimbaled. They are fixed to the airframe, and they change their orientation as the aircraft maneuvers. The accelerometers are also in fixed positions, longitudinal, lateral, and normal or vertical with respect to the airframe. A system where the gyros and accelerometers are fixed to the airframe and maneuver with it is called a strap-down system. This is in contrast to INS, which was a gimbaled system. The ring laser gyro measures angular rotation. Unlike previous methods, there is no system of comparing a gyro with gimbals in order to measure an angle. It is a completely new principle to us, and it depends on a property of light known as the Sagnac effect. Suppose that we have a circular tube and that we can send light round it in both directions. If the tube is stationary and we start both beams at the same time, they will arrive at the same time. However, if the tube rotates during the passage of the light beam travelling in the same direction as the end point in the tube takes longer to arrive, and the one travelling in the opposite direction takes a shorter time. We can measure this difference in light path and use it to detect rotation. In this, it is difficult to make light travel on a circular path, but the same effect is achieved using straight light paths reflected by mirrors into a triangular pattern. Also, in practice, when dealing with the speed of light, it is not possible to measure such small differences in time. We can, however, measure a frequency shift between the 2 beams. The ring laser gyro utilizes the Sagnac effect. It is basically a triangular glass prism containing drilled tubular cavities. This is a cathode. Its function is to emit photons, which are minute particles of light. There are 2 anodes, which are of opposite electrical polarity to the cathode. A large potential difference is maintained between the cathode and both anodes, which causes the photons to be powerfully attracted towards the anodes. The potential difference between the cathode and each of the anodes is the same, and so the photons are equally attracted to both. The light therefore divides, approximately half of it travelling clockwise and half anti-clockwise. The drilled tubular cavities are filled with a helium and neon gas mixture. This acts as a conducting medium, and so the light is channeled down these specific paths. One of the defining characteristics of lasers is that they produce what is known as coherent light, that is, light at a single frequency. Normal light, such as sunlight or light from an electric bulb, is usually known as white light, but it actually contains all the colours of the visible spectrum, which are all at different frequencies. Laser light is not like this. It is one colour only, usually a kind of pinkish orange, and each beam has only one frequency. The continuous circulation of the light in each direction has an amplifying action which builds up to a saturation point. At this point, standing waves form. When this happens, it is called lasing. This lasing can only occur if there is a whole number of wavelengths in the path distance. This determines the laser light frequency, which will be the same for both the clockwise and the anti-clockwise light in a stationary prism. However, if the prism rotates about its sensitive axis, the number of wavelengths in each path length remains the same, but the path lengths change. This means that the frequencies must change. Conversion of the frequency change into a measure of angular rotation rate is achieved by use of interference pattern technology, which is explained in the next scene. Interferometry is a measurement technique used in various scientific applications, such as X-ray crystallography and radio astronomy. An interference pattern is formed whenever two beams of light or any other form of wave motion converge on a single point. Let's start by explaining it with water. Imagine that a brick is dropped into a pond. Circular waves of ripples will radiate out from where the brick went in. As seen from sideways on, the waves will look like this. A cork in the water would stay in the same place laterally, but would bob up and down as the waves pass through it. There will be peaks and troughs. As seen from above, it will look like this. Now imagine that two bricks are dropped into the pond simultaneously. The wave pattern will look like this. Here are the peaks and troughs. Now imagine that this is light, not water. Where two peaks meet, there is a build-up of intensity, and in between, it is darker. Now let the light fall onto a screen. We get a pattern like this. With two light sources at the same frequency and phase, the pattern remains static. But if the frequencies alter, the pattern moves. The direction and rate of pattern movement are a measure of the aircraft's rotation direction and rate. The laser gyro contains a photoelectric detector. It can tell if the interference pattern is static, and, if it is moving, it can detect the direction and rate of rotation. One problem associated with the ring laser gyro is called laser lock. The two laser beams can synchronize and, if this happens, they give zero output even when the aircraft is altering its attitude. A piezoelectric dither motor therefore provides a constant input of vibration at a known frequency, which prevents laser lock. The same signal also has to be sent to the computer to tell it to ignore the introduced vibration and simply measure the difference between the dither motor input and the laser gyro output, which is the desired measure of angular rotation. Let's sum up this second lesson on inertial reference systems. We said that the biggest single change which makes an IRS different from an INS is the use of ring laser gyros. These ring laser gyros are not gimbaled. They are fixed to the airframe and they change their orientation as the aircraft maneuvers. This is known as a strap-down system. Ring laser gyros measure the Sagnac effect to establish angular rotation rate in pitch, roll and yaw. Lasers produce coherent, that is, single frequency light. If the prism rotates, the number of wavelengths in each path length remains the same, but the path lengths change. This means that the frequencies must change. The two light sources arrive on a screen where an interference pattern is generated. With two light sources at the same frequency and phase, the pattern remains static. But if the frequencies alter, the pattern moves. The direction and rate of pattern movement are a measure of the aircraft's rotation direction and rate. Ring laser gyros suffer from laser lock, but the problem is avoided by use of a piezoelectric dither motor. That concludes this lesson on the ring laser gyro. The next one looks at how the angular rotation rate information is referenced to the horizontal and to direction on the Earth.